Welcome to The Explainer. Today, we're putting on our invisible X-ray glasses to uncover the microscopic drama that's unfolding all around us, literally every single second. We interact with the physical world constantly, but we rarely stop to actually think about the invisible mechanics making the whole shebang possible.
Let's jump right into this mystery. Have you ever wondered why a solid stone keeps its exact shape when you plop it on a table? But an invisible gas leak from a kitchen stove can just spread everywhere and fill up an entire room in mere moments? They feel like completely different real-world events, right? But actually, they're driven by the exact same underlying scientific rulebook, the particle model of matter.
Section 1. Meet your matter, the basic building blocks. To really understand our world, we've got to introduce the three main characters of our microscopic universe. Everything around us is made of particles, and their behavior completely dictates whether a substance is a solid, a liquid, or a gas. Right off the bat, look at how solid particles are tightly packed together. They're totally fixed in a specific place. But, here's a really common misconception. People often think solids just don't move at all. Well, actually, scratch that. They do. They just don't flow freely. They simply vibrate right there in their fixed positions. And that rigid, vibrating structure is exactly why solids so stubbornly keep their shapes. Now, let's move over to the liquid phase. Notice how these particles are still pretty close together, kind of similar to solids. However, they aren't locked into some rigid grid. They actually have enough freedom and spacing to just randomly slide past one another. And it's exactly this sliding motion that allows water to be poured out and perfectly take the shape of, say, your favorite coffee mug.
And then we have gases. Look at all that space. Gas particles are incredibly far apart and move completely freely in all directions. They have absolutely no definite shape and are basically living their absolute best, most energetic lives out there, expanding to fill whatever container or room they're put into. Just think about when you inflate a balloon. The air immediately spreads out and pushes against the entire inside of that balloon.
So what does this all mean? The absolutely crucial point here is that behavior at the macro level is entirely dictated by rules at the micro level. A stone holds its shape on your table because of incredibly strong attractive forces, keeping those vibrating particles firmly locked together. Meanwhile, water changes shape instantly when you pour it into a glass, simply because its particles can easily just slide right past each other. Section 2, adding heat changes everything. Okay, so now that we know our basic building blocks, let's see what happens when we introduce our invisible catalyst into the mix, heat, energy. Heat is essentially just adding energy into this microscopic system. Let's ground this in a real-world scenario for a second. Imagine Mang Jose out in the barangay selling hard, solid ice candy in the morning. It's perfectly frozen, right? But by noon, the blazing sun is just beating down on his cooler. And that hard ice candy transforms. So what is actually happening to those particles? Well, the heat from the sun basically acts as fuel. It gives those tightly packed, vibrating solid particles the exact burst of energy they need to break out of their fixed positions. And once they break free, they start sliding past one another. Just like that, the solid has officially become a melted liquid. The exact same heat effect happens when Anna washes her clothes and hangs them outside on a beautiful sunny day. Over a few hours, those wet clothes become completely dry. Why is that? It's because the liquid water particles trapped in the fabric are absorbing heat from the sun. They gain so much energy that they evaporate entirely, moving straight up into the air as a completely free-roaming gas called water vapor. And, if we aggressively add stronger heat, the results are even more dramatic. Think about a kettle of water boiling on a hot stove. As we literally pump heat into the water, those sliding liquid particles gain immense energy. They start moving drastically faster, spreading further and further apart until they turn into steam, violently escaping the kettle as a super fast-moving gas. Section 3, cooling down and locking in. So, if adding heat frees particles up, what happens when we do the exact opposite? What happens when we remove heat energy to kind of lock those particles back into place? Picture a really cold glass of soft drink sitting on a table on a hot, sticky day. You know how the outside of the glass gets all wet? That's definitely not the drink leaking through the glass. The warm air around the glass actually contains invisible water vapor, and when those free-roaming gas particles hit the cold surface of the glass, they cool down and rapidly lose their energy. This is condensation in action. As the gas particles in the air lose energy from touching that freezing cold glass, they slow right down and start to clump together. They immediately lose their free-roaming status and become those sliding liquid droplets you see right on the outside of your drink. Now, let's take it a step further. Imagine putting a tray of that water right into the freezer. You're continuously removing heat at that point. Those sliding liquid particles are losing even more energy, slowing down until they become completely fixed in position. Bam! They are now officially locked in to the solid structure of ice, returning to that state of mere vibration we talked about earlier.
Section 4. The power of invisible forces. There is this absolutely vital relationship between particle spacing and attraction that, quite frankly, can literally save lives. It's pretty simple. The closer the particles are, the stronger the attractive force between them. This perfectly explains why solids with their tightly packed particles have incredibly strong attraction and are so incredibly tough to break. Liquids sit in the middle with a moderate attraction, and gases, well, because their particles are so far apart, they have very weak attraction, which is exactly what allows them to roam entirely free.
And this directly brings us to a critical, real-world scenario regarding LPG tanks. We all know many families use liquefied petroleum gas for cooking in their homes. And as the source explicitly notes, even a super small amount of leaked gas can spread around the kitchen rapidly, even if it's completely invisible to the naked eye.
Because gas particles have such weak attractive forces, are incredibly far apart, and move freely in all directions, a tiny leak doesn't just stay near the tank. It aggressively expands to fill the entire space. This really proves that knowing your physics isn't just about passing a science test. It is literally a vital matter of home safety.
Section 5. Real-world particle survival. Let's consolidate our new X-ray vision into one ultimate cheat sheet. Think of this as the master rulebook for the universe around you. For solids, the particles are close and fixed, vibrating rigidly right in place. For liquids, the particles remain close, but they finally have the freedom to slide past one another. And for gases, those particles are far apart and move completely freely with very, very weak attraction. Master these three states, and you basically master the mechanics of matter itself. So I want to leave you with this final thought. Armed with this new perspective, just take a second and look around your space right now. From the steam coming off a hot cup of coffee to maybe some condensation on a nearby window, what kind of microscopic particle drama is unfolding right before your very eyes? It's pretty wild to think about, isn't it? Thanks for joining this explainer, and until next time, keep looking deeper into the world around you.